Good evening, everyone. My name is Eric, and today I'll be talking to you about the evolution of medicine throughout history. Um, I've watched the last online presentation, and I can tell you this one is a bit shorter and less technical. The objective here is to somehow introduce you to a small fraction of what is it possible when talking about AI in medicine. So the key points of the presentation are the beginning of MedTech, where did it all start? Then we'll move on to evolution of technology. How did it impact the field of medicine? Then I'll be giving you some examples of how AI can directly influence the medical device. We'll be talking about bionics and prosthesis. Then I will present something about my third year project, detecting and predicting epileptic seizures. And in the end, I've pointed out some papers, publications on the current state of research in medicine right now. I didn't really include information about the new coronavirus because it's a hot topic right now. And my intention is to tell you about the general thing in medicine and AI, not the hot topics. Okay, so the question is, where did it all start? We're gonna look at old medical device. I've got a question. Does anyone know what this represents? What this object is? I'll be waiting a bit because I know you have to unmute your mics and then talk. Yeah, it's one of the first stethoscopes invented and actually working. It was invented in 1816. It is not really powered by any electricity or programmed or anything, but it gave society the will of searching for new things in the fields of medicine. As a result, about 8 years that we've got the first X-ray. It was a bit noisy, but a big step in medicine. And after that, we got in 1975, 79, the first CT scan. Again, noisy, but it worked. And the first pacemaker, heart pacemaker. During both World Wars, medicine has made incredible advancements, and that's the reason why we arrived where we are right now. Here's a list of inventors, a small fraction of them. Almost everyone got a Nobel Prize. So as I said, the first stethoscope in 1816, then we've got the discovery of the X-rays we've seen before in 1895. And a bit after that, we've got the first heart monitors, pacemaker, defibrillators during 1950s, right after the end of the Second World War. As a parallel, during this time, technology advanced with small steps. We've got punching cards, which were used in the late 1800s. They were literally cards with holes in them. They were used to store patient records. And after that, we've got tabulating machines. Basically, these were used to sort a big amount of data and to store them. They were reading these cards and to store the information. This procedure enabled a better statistical information. which was used specifically in epidemiology and population study. As a result, in 1950, based on a large data set, the most important finding in 20th century published, and it showed that between 1922 and 1947, lung cancer rose by 1,500%, which is enormous. It was a direct indication of the correlation between smoking and lung cancer, because at that period of time, doctors prescribed cigarettes for anxiety, depression, and other diseases, and they weren't really aware of the damage they were making. Now we move on to modern healthcare. Nowadays, we've got CT scans that can reproduce organs, all the organs in your body, including bones, bone structure, veins, nerves, anything you want. And this is a good application of AI. So you can basically diagnose many diseases using CT imaging. You can apply all sorts of deep learning algorithms, machine learning, and etc. We've got clear X-rays with small amount of radiation. This is a huge improvement because when first X-rays were used, and when people started using radiation as a cancer treatment, they weren't really aware of the damage that radiation was making. And because of that, while they were curing cancer, they were creating other forms, other cancer cells. So they basically were killing people by treating them. Next, we've got pacemakers that are more accessible and portable than ever. This is another huge step because now people can detach from stable pacemakers and go outside and don't worry about staying next to a device that powers their heart. And probably one of the biggest thing is online fire records, which are easy to access. This is a big thing because of this, we can store patient information, and we can use the data sets for machine learning training, deep learning training, training our algorithms, research, etc. So it's a very important thing. Obviously, we have to take care about patient information and all that things. But so with the evolution of technology, we can consider applying different algorithms that positively impact and improve medical research and the overall views. Next, we'll be talking about another thing, big thing, the Da Vinci surgical system. This system was initially designed for US military. There aren't many that know that, but I've been to a conference, and the CEO that designed this, that took part in designing this, told us, the participants, that it was initially designed to make surgeries on the battlefield, so that surgeons don't have to risk their lives going there. But due to the lack of technology that was back then in 2000, even 1998, 1999, they couldn't really achieve that, and they left it as a prototype, which was picked up as a invasive surgery method. So it didn't use at the beginning, any form of AI, but it used methods to transform movement from the surgeon into precise and accurate movements, eliminating noise. The big thing is that the joints could move 360 degrees, having 7 degrees of freedom, which is a much better configuration than a normal human hand. Simultaneously, it presented a 3D representation of the surgical area displayed for the surgeon. So this is a general setting. We've got here the surgeon controlling some sort of you can call it joystick, but it's not really that. It's much more complicated. It's basically a hand. He could watch the surgery on a 3D images with 3D images of the operative field. Those images were also available on the OR monitor. The movements of the surgeon were transmitted to the robot. And as I said before, it had 7 degrees of freedom. It mimics the human hand and wrist. And here, let me show you. It's a diagram. Basically shows one of the essential processes, the robot, the pressure and the force movement control block. So basically the surgeon hand movement, so the surgeon applied the force, which was translated to the tools it used. The translation involved within the control system included scaling large hand movements to smaller movements while eliminating noise. And the surgeon was able to feel physical boundaries due to the sensors that were fixed on the tools, which is a big thing because imagine tools having sensors in it, and each surgeon was aware of the movement of the robot and the boundaries it created. So basically, from the transmitter, the information was given to the receiver via Bluetooth, and also to the user interface on the OR monitor. And it gave feedback. So each time the process was filtered using anti-jitter data processing, and finally the pneumatic system was gave the information to the motors. Now, I assume most of you have seen this, but I didn't really want to show you an actual surgery because maybe not all of you like that. I think to focus on is the precision of the device and how accurate the movements are. So all of this is controlled by the surgeon. And imagine how precise things have to be in order to peel a grape like that. And also there are basically three hands that are doing is holding the grape, and the other two are cutting it and peeling it. Okay, now the question is, can we further improve robotic surgery with AI? There are four main aspects we consider when talking about improvement of the robots. The first one is preoperative planning. So you have to plan the surgical procedure from existing records and before the actual surgery happening. There's a list of requirements here. The prediction and detection of the disease, classification of the disease has to be accurate. privacy has to be secured, and the speed of the preoperative planning as is objective. The challenge is basically multimodal input. There's a patient diversity and complicated symptoms. And we can consider sub-areas such as classification, detection, segmentation, and registration. And we can use algorithms, AI algorithms, such as we can use deep learning, convolutional neural networks, and recurrent neural networks for anatomical classification, detection, and as I said earlier, segmentation to image registration. The big challenges that we face right now are, so we need a large annotated data set. I will mention this many times during this presentation. This, perhaps many of you know, this is a big thing. You can't really use AI if you don't have a large data set. And then not all algorithms can be applied clinically, because there is a difference between medical and natural images. For example, you can train your algorithm on clean images, filtered images, pre-processed ones, but during the procedure, let's say your blood vessel pops and you've got blood everywhere, and your algorithm doesn't really know what to do in that situation. Next, we've got intraoperative guidance. For robotic surgery, we need to provide visualization and localization during the surgery. You have to be aware of the exact position of the robotic arm. Here again, we've got, as a requirement, we have to have a real-time prediction, precision, and high resolution of the things happening. A few challenges, of course: low resolution input of the cameras, tissue deformation, or less visually accessible environmental variance. And as algorithms, we can use PCA, statistical shape modeling, partial least square regression, GAN, CNN, RNNs. And again, challenges: we need a lot of label data for training and testing, and some algorithms cannot generalize for certain procedures. That's because some surgical scenes are textureless, are being difficult to extract features from, and then again, your algorithms won't work as expected. Next, how can we improve the robot itself? This task is by using AI. We can make robots understand the complicated surroundings, take decisions by themselves in real-time environments, and we have to consider robustness and safety. And now, as an algorithm for that, reinforcement learning seems to be this most common one. What happens here is you're basically programming your robot to take decisions by itself, and then based on those decisions, you gave rewards, positive or negative rewards. Now, the things to consider are, it requires generalized learning. There are multiple scenarios, types of surgeries. Needs to be integrated with surgical workflow. There has to be a consensus between the surgeon and the robot. You cannot leave them fight each other. The robot has to agree with the surgeon and vice versa. And now we move on to ethical and legal issues. Uh, in every application of AI, we're dealing with this. There has to be a privacy, medical records have to be secured, gene data, illness prediction. Again, it requires high level of security. You cannot have problems with your data protection. Cybercrime impact, if a failure happens, you have to be sure that the impact of the patient is minimal. You don't want the patient to suffer because of mistake your robot made or the software designed the robot. It requires a thorough risk examination. And after that, we have to build trust between humans and robots, because there are many cases in which humans don't consent to robot surgery. Okay, we move on. Yeah, so ethics that impose to use new technologies responsibly. We move on to bionics in medicine. This is another, let's say, area. Are there any questions so far about the things that I've said? Again, I'll be waiting a bit for, if not, then I should continue. Okay, so let's just skip the question for the end of the presentation. I think it's the best approach. So the first evidence of prosthesis goes back to ancient period, around 3000 BC in the ancient Iran. This image is from, so this prosthesis was found in Egypt in around 1000 BC. You can see how carefully it was made. Even the fingernail was reproduced. And this is an image of the current state of the art bionic arm. So how does the current bionic work? We can classify the working process of any artificial limb in 3 categories. So you have to read the input that the muscle or the part of the limb gives you. You have to process that input, and you have to act. So the bionic arm has to act according to the computed signal. Now, you may ask, how can we apply machine learning or deep learning in bionics? So the main reason is to control the fluency of movement, successfully classify and predict the type of gesture desired and the direction desired. This is a general artificial limb, nothing special about it. But the idea is so you know how it works. The first, in this socket, you have electrodes. The main purpose of them is to read the electrical signal, which and pass it to the next step. That electrical signal is being sent from the brain down to the spinal cord and then all the way to the muscles. And your signal is read by electrodes. Next, the processing the input part. The signal is given to the control system, which is processing the input. Usually, the input that you read from muscles is very low, so it usually is you can really differentiate from the noise. So you have to amplify the signal um, and filter the noise, compute and adjust the power you send further to the motors. And this is where machine learning comes into play. So after you've read the data from the muscle, you basically estimate the output, you predict, you classify the movement uh, the patient wants to do, and then it's a loop. Basically, give it to the hand, and the feedback goes back to the algorithm. In this video, you'll see the difference between an embedded system, which uses some machine learning algorithms, and a conventional system which doesn't. Take a look on the precision of the movement of the patient and the accuracy of the movement. As you can see, the conventional control struggles with perceiving the input given from the muscle. Thus, the action is much slower. Okay, so more advanced bionics and exoskeletons. Now, the question comes, what does a patient do when they're paralyzed? Because, as I mentioned previously, the way a bionic arm works is reading the impulse coming from the brain to the muscle and then perceiving that current, low current. But if the patient is paralyzed, that means somewhere in the spinal cord there's a small section of the nerve. Thus, you can really read the input because the input doesn't really go to the muscle. So in the first, so more advanced bionics are reading the input directly from the brain using electroencephalograms. The procedure is basically the same. You put electrodes on the scalp of the patient, and those electrodes pick up signals from the brain. And as you can see here, the patient is not really moving his arm, his muscles. Oh. Okay. And they're using a VR system to visualize the actual actions he's doing. So you can see the arms are not connected to the patient, but they can still move even from picking up signals from his brain. And here, this is a paralyzed guy. They build an exoskeleton that can read brain activity. And again, nothing to do with foot movement, arm movement, and general body movement. Everything is picked up from the brain. And okay. And he's able to move using this exoskeleton. And this is really a huge step towards building some sort of, I know it sounds which sounds weird when I say some sort of a Iron Man suit that, who knows, when you use it, you can move faster, better, stronger, whatever. Now, I wanted to show you how you can control others with your brain. I'm not really sure if many of you have seen this. Um, it's basically on what I have said earlier. Your brain gives nervous impulses to your spinal cord, and then uh, that small current goes through your body to the desired muscle to do a certain movement. And okay, so let me go back a bit. How this thing works, to summarize, I didn't want to let you, if you're interested, just go to the link. I'll give you the presentations and you can follow up. So the way this works is this woman is connected to a device with electrodes. She's doing different arm gestures. That device picks up the current and passes it to this guy's arm. So basically the same, I mean, it's not really the same electrical signal because it obviously is amplified, but you'll get the point. Yeah, so exactly what I was telling you, the brain has to do it. The question is, again, how does the brain do it? It sends the information to the arm, and that's why paralyzed people can't really use those types of bionics because uh, it's not supposed to work that way. Okay, now we can move on to my third year project on detecting and predicting epileptic seizures. I will not tell you many details about it because it's not yet published and I'm not really allowed to speak very detailed about it, but hopefully you'll get the broad picture of it. Um, for those of you who don't know, what are epileptic seizures? So a seizure is an uncontrolled discharge of electrical impulses that affects the cerebral cortex. Now, the cerebral cortex is one of the most important structures of the brain. Uh, in that place, all the external information is processed. So it conducts around 100 trillion synapses. So imagine an uncontrolled discharge of electrical impulses affecting 100 trillion synapses. Your brain will go wild, and your entire body will do. Worldwide, it affects around 65 million people, and then comes the diagnosis of epilepsy. So if you have a seizure and that's it, you can move on with your life, and yeah, nothing that really that bad. But if you've got epileptic seizures, then those seizures are recurrent. So it will affect you over and over again, maybe 3, 4, 5 times a day, which is really a bad thing. And different parts of the brain may be affected. Thus, the corresponding sensorial perceptions can be temporarily altered, like field, touch, sight, equilibrium. So if you think about this, so if you have an epileptic seizure, if you have a seizure, then your body will lose the sense of equilibrium, the sight. You won't be able to feel anything. You'll fall down. So it's a really serious thing. Imagine being in a car and it just happens. That's how many people die from seizures. There also have been cases where severe seizures attack even led to patients' death. They're called SUDEP, sudden unexpected deaths in epilepsy, and basically very severe seizures just cause death, and it's really a really weird event. Now, we will be looking at effects and treatment. Why is this so concerning? So more serious seizures can irremediably damage the brain. You cannot go back to the state of the brain before seizure if it's really bad. Being uncontrolled electrical discharges means it could happen anytime. Thus, there's a huge risk of accidents. As I mentioned before, you can't really go swimming or whatever in a pool because if a seizure happens, then you might get injured or even die. And also another thing to consider is patients will usually develop anxiety and depression because they don't really know when it's going to happen, the seizure. They know it will, but this affects their lifestyle a lot. Now, how can we be cured? The most common approach, obviously, is treating seizure attack by inhibiting it, taking prescription drugs. An anti-epileptic drug can control, so they're called anti-epileptic drugs. They can control up to 70% of the patients. However, there's uh, nothing to do about the other 30%. There are also other possibilities such as brain surgery and vagal nerve stimulation, but obviously the risks are greater. You don't really want to mess up with brain surgery. Now moving on to the benefits of detecting and predicting a seizure. So obviously, if you do research in a field, then you may discover some new things. A closer and thorough examination of epileptic seizure can represent a step towards a better understanding of the phenomenon. And also the main goal and the main goal of the project is that you may be able to introduce the two algorithms of predicting and detecting seizures in devices, in portable devices, so that those could inform patients of an imminent attack, and the patients could take the necessary actions to protect themselves. Now, a good prediction could save thousands of lives, and as I said, the algorithms can be implemented in portable devices, and the patients could improve their lifestyle greatly. And devices could help storing the information and building towards a greater data set. As I mentioned, I think 3 times before, the most important, or one of the most important things in AI and in general machine learning and deep learning is to have a stable and a large data set. And if you implement those algorithms, you can keep track of the data and build towards a more developed data set. Okay, so my proposed architecture and the one I'm currently working on follows 4 steps in a broad description. I'm processing the data, then I'm using convolutional neural networks for detecting seizure attacks, then moving on to recurrent neural networks, specifically long short-term memory cells for predicting future attacks. And then the goal is to select the smallest number of channels for a good prediction. It's really hard to define a satisfactory prediction, but usually it's more than the average chance, obviously. So in a couple of slides, I will show you how the input looks like, how the EEG looks like, but that's the input I'm using. So raw EEG goes to pre-processing and feature extraction. I'm basically eliminating noise, considering the required channels. I'll talk about that in a minute. Then moving on to the convolutional neural network, recurrent neural network, and I've got the prediction of the attack. Let's talk about the input data in the EEG. It represents raw readings of the brain activity collected using an electroencephalogram. This procedure is made by placing electrodes on the scalp of the patient. Also, there are other types of EEGs. They're called interictal EEGs, and they're basically taking the brain activity directly from the brain or the scalp. So they're making some small holes in your scalp and placing those EEGs. They're a bit more accurate. You don't have the that big of a noise difference, and the signal is much more powerful. I mean, higher. Each electrode picks up an electrical impulse coming from the brain. This is a common it's called 10-20 configuration of EEGs. Basically, each circle represents an electrode. And for each lobe, you've got a different electrode. For example, this is the frontal parietal lobe, frontal lobes, parietal lobes, etc. The central ones, temporal ones, occipital ones. The way the input is pre-processed, we don't really take the input of each electrode. We differentiate from, so make a difference between the voltages from one electrode to the other, the difference of voltage, and that's how the data set is created. Here you can see a raw EEG. So the circled area is a more severe seizure attack. So there's an interesting thing to mention. The actual seizure started on the second 31, I believe. This is 54. So all this information is while the patient has a seizure, and this is a bit that is more severe. And as I was telling you earlier, these are the channels, and you don't really take each channel as an input. You want to make a difference because you want to reduce the peaks, you want to reduce the noise, and that's how you're doing that. Okay, so challenges and the main features of the data set that I personally am using. The biggest challenge is that of this approach is that each human has a different brain activity, which means you cannot generalize the findings that you get from a patient to the one you're getting from another patient, which makes things a bit trickier. You kind of need a personalized algorithm for each individual. It is, as I said, nearly impossible to be certain, like 100% certain with a prediction on what impulses can or cannot cause seizures. Another important thing, external factors have to be considered. You don't really see this in many data sets because obviously they're doing in clinics. There might be certain activities that can trigger your seizure, and obviously they're not doing those activities while taking the data set. Severe seizure signals for some patients may not even represent a seizure for others, which means if someone has a small seizure, then other patient may not even have a seizure with those specific configuration, like electrical configuration. The data set that I'm using comes from the Temple University Hospital, which has around 850 gigs of pre-annotated seizure recordings. If you are interested, I can help you get your hands on this data set. They've just updated it. Besides the actual EEG data, other useful information for training the networks are drug prescribed for seizure controls. So you want to take into consideration what drugs the patient is taking, because that might affect the input, the age of the patient, the weight, seizure, and the seizure frequency. It's not really it's not really updated on a regular basis. I mean, you should define a regular basis. I think the last update was around, if I'm not mistaken, 6 months ago. So and I think 3 days ago it got updated. So it's pretty, they're still working on it. And they're planning further updates. Okay, so now just a few things on the current state of the art research in MedTech using AI. I just bullet pointed some interested articles. As I said in the beginning, I didn't really want to focus much on the coronavirus because it's a hot topic right now, and I just wanted to present the broad picture. So obviously they're doing deep learning system to screen coronaviruses, pneumonia, estimating the uncertainty and interpretability of data learning for coronavirus and other stuff that is not really related to coronavirus, but they're using AI in medicine. And that's about it. If there are any questions, either in Romanian or English, I don't really mind. You can ask me everything about the presentation.
Cool. Thank you, Eric, for the presentation. So any questions, verbal or written? So there's a question from Alex in the chat. Alex, if you want, you can also unmute you and ask the question.
I haven't really seen that article, but I'll be taking a look over it.
Okay, thanks. Basically, they say they also train for each patient.
Okay. Yeah, I'll be taking a look on that article. Thank you for sharing it. Are there any other questions? Even in Romanian, it doesn't really chat or everything.
I know there are problems with applying AI in medical medical because of privacy issues and data sharing. Companies don't want to share data, and they are still working on federated learning and other schemes to be able to share data without actually sharing.
Yeah, there's a big concern about this. So I'll be answering Christian's question in a minute. Yeah, there's a big thing with privacy. So last summer I was working with one of my professors, and the original idea was to try to predict and detect certain asthma attacks. But the thing that hold us was the lack of data sets. We were supposed to work with some medical units from Singapore, but they told us that the data set will be available in the fall of last year, so we couldn't really work on that. Yeah, indeed, there's a huge issue with data privacy, data protection, which affects AI greatly. And Christian asked, in order to detect a seizure, the patient must wear the electrodes all the time. Yeah, so that's the idea of the project, because otherwise you can't really. So the idea is to make a device, electrode-based device. So you should wear that device all the time, and because otherwise you can't really read the brain activity, so you can't really know what's happening in there. Okay, any other questions?
There's another question in the chat.
Okay. So the signs are not reflected in other organs. Not really. So in order to be as accurate as you want, you really need to read directly from the brain, because if you remember, I said a few moments ago about Bionics, and that they're using electrodes directly from the brain because maybe some patients are paralyzed, or the EEG coming from the brain is much more accurate, and you want to filter out the noise. And yeah, that's why. About the are there any good electrodes? Yeah, so electrodes don't really, not really sure that they affect the tissue. I'm not really sure about that.
Yeah, I know they are still researching good electrodes because they need to be soft, because it's the tissue surrounding is very soft, and they need to move with the tissue, and also they need to be biocompatible. Also they need to be very small. Also they cause inflammation, and it doesn't stay a lot of time. After a few weeks they need to change
to replace them.
replace them, so it's not practical.
Yes, I'm not really aware of the state of research on electrodes, but yeah, that makes sense. Yep. Anything else? Also, there's a list of references if you want to look up on stuff I've read.
After the presentation, almost any previous presentation is also attached to the event box on the community website.
Yeah.
So if that's okay with you, I can also attach this one as well.
Yeah. And also, if you want to, I've seen a slide right here to give feedback on the presentation, please feel free to do so. Okay, are there any other questions?
Guess not.
I guess not.
The presentation. Thank you, everyone.
Thank you, everyone, for attending, and stay safe with the coronavirus.
Sure.
Thank you.
Thank you. Bye.
Bye.